I posted code for how this particular shape could be made using all the squares from 1 to 2112 twice. This is based on Adam Ponting's square packing method, which I will get to later in the discussion. But since I updated it with correct code, I made some typos when I typed the code in 12 years ago or thereabouts. I figured I would update it. Also, there's been many recent new discoveries in packing over at Eric's Packing Center, which is at this address. And one example is this packing, which should have been found many years ago. Here's another one found in May. A new best way of packing that many squares into a circle. And a new best way for packing 10 triangles in a circle, found in June. And a new best way of packing 45, 45, 90 triangles, 7 of them in a circle. And just 4 in a triangle wasn't found. This new best method wasn't found until May. And a new method for packing this many squares into a triangle, and even a few ways of packing hexagons into a square weren't optimized until just recently. So with a whole bunch of different packing results and the update there, I figured I would cover squared squares. And that's where it gets strange, because the squared article by Martin Gardner, which I'll be showing very shortly, was written up by William Tutt, and Martin Gardner pretty much just used William Tutt's discussion of the whole problem as his column. Another problem that William Tutt worked on was the cycle double cover conjecture, and in that you can basically boil the problem down to snarks, a type of graph where all vertices have exactly 3 edges, but you cannot color the edges with 3 colors without having 2 of them meet at a vertex. And this is a special type of graph that Martin Gardner called snarks, and the name stuck. So the cycle double cover conjecture can be boiled down to whether you can always do a double cover on a snark. One example of a double cover, if you take a cube, the 6 faces of the cube each will hit every edge of the cube twice. So the double cover is basically whether or not for all graphs there's something similar to what happens with polyhedra, that there are sets of cycles that cover every edge twice, because polyhedra do that automatically with their faces. And this has been a long unsolved problem until last Saturday, where OpenAI announced that it had a proof. So I asked OpenAI to provide code for me that followed the algorithm in the paper. And after various iterations, I finally nailed it down, and it's on Community now, code for rendering any cubical graph as a double cover. And one part of that discussion on Community is I do it for 300 and something snarks. I provide the double covers for all of them. And here's an example of one, the flower snark. And here's some various related links for that. This whole talk, by the way, will be on, well, it's already on Community right now. If you go to Wolfram Community, it should be on the front page, the whole talk I'm about to give. Let's see. I also have updates for the problem I discussed last week, the no 3 in line problem. There's been some more there's been more solutions found. And in fact, there was a paper in 2022 that also had solutions. So basically, we've verified everything in that paper and built on it. Here's the new set of best solutions. And I've also updated the code to some extent. I believe that this solution is still optimal, is still the largest known for the maximal no-3 inline problem. At least it was, and when I checked a few hours ago, but in the last talk, 70 was the best until I started giving the talk and they updated it to 72 during the talk. So these are the best solutions up to some size. These are the minimal problem. It's impossible to add another mark anywhere in this grid on an empty square without creating 3 in a line for some set of 3 points. And you can see some of that with this code where I put in the lines that provide a complete coverage. And this is also on community and it's interactive. So for example, this point is covered by these 2 points. I also have code on demonstrations for the maximal problem where I show the initial solutions. For example, that's the smallest. I need to update this one to include the new results. Another item dealing with squares that I worked on is I saw this famous image from the 80s, but the version from back then has gone through so many different copies and copies and copies in different formats that it looks terrible now. So I thought I would update it using AI. And it did a terrible job. It took about 20 iterations and it still looked terrible. It looked okay, but the comment that this color and that color were the same wasn't correct. And so this was finally fixed in Photoshop because the AI couldn't get it quite right. This is the Craig O'Brien corn sweet illusion. So I've been doing all these things with squares, so I thought I would look back at Martin Gardner's second book where he talks about squaring the square. And he discusses the people that were involved with this back in the 40s, Brooks, Smith, Stone, and Tutt, each one of which wound up being famous in different ways. And here he discusses the algebraic way of solving one of these, but this wound up being too difficult to do for hundreds and thousands of cases. So Tutt developed another method based on graph theory and electrical networks. So we can do that with Mathematica code. For example, here's a particular graph. I have various candidates that have various properties. And I picked a few graphs that were able to do multiple things at once. So here's one of the graphs. And basically, we pick a planar graph. All of these things with squares deal with planar graphs. And one edge is selected as a pole. You try to solve the equation here using electrical networks. And one thing to notice is that for each edge, for example, here's a 25 here. The 25 leads down to 9 and 16, and 9 plus 16 is 25. So basically, each time an edge enters a vertex, the values leaving the vertex sum to the same value. And that allows you to get a squared rectangle. So here we have our candidate graph, and we have to solve that. And that is done with something called a Kirchhoff matrix. And with this set of graph edges and currents, we can get these integer sides for a particular solution to solve the Kirchhoff potential problem. And there's a code for all this in the discussion on community. So once we have the solution for the graph, we can draw the squared rectangle directly. So here we have the graph here. The 7, each vertex here corresponds to one of the edges of the squared rectangle. So the 7 corresponds to this top edge. The 3 here corresponds to this second edge. The 1 corresponds to this edge. And for example, from 1 you can go to 6, which corresponds to this edge, and then 2 is the bottom edge. And if you have a whole bunch of planar graphs, you can generate all the possible squared rectangles that those graphs can produce. There's another concept that I've brought in for a different problem where you take this solution. So here we have a set of squares. We just basically crush those squares into simple rectangles. So here are the various rectangles corresponding to the previous item. So not all of these diagrams are solvable as squared rectangles. For example, if you just have one squared surrounded by 5 dominoes, that one cannot lead to a squared rectangle. If we have a particular crush topology, it's possible to do it as a squared square, but also it's possible to do it as what's called a Blanche dissection, where all the various rectangles have the exact same area. And this is something that was a concept developed by somebody named Blanche Descartes, which was a pseudonym for William Tutt, the person I mentioned at the start who wrote Martin Gardner's column. But he also wrote a whole bunch of recreational mathematics under the pseudonym Blanche Descartes. And there's the smallest Blanche dissection where a square is divided up into rectangles of the same size in a non-trivial way needs 7 rectangles. And you can find, if you look for Blanche dissection, you'll find the 7 rectangle solution. But there are many different rectangle sets which can lead to Blanche dissections. However, not all are solvable. There are many planar graphs which have rectangle diagrams which do not solve a squared rectangle or a Blanche dissection, and sometimes not either. To look at these, basically all you need to do to find all the solutions is to look at all the planar graphs. And that has been done to some extent. A lot of these planar graphs have been done thoroughly up to some, I'm not sure how far it's gone yet, but these are the number of planar graphs available to use for this problem. I believe it's all done up to planar graphs having 30 edges or less. And most of those are at squaring.net, which has a catalog of all known squared rectangles and squared solutions. Here are some sample perfect squared squares of orders 21 to 30. And in these cases, these are the smallest that are known. And we also have the largest that are known for each of those orders. These are represented by what's known as a Bouwkamp code, which I'll cover very shortly. So one question Martin asks, or William Tutt asks, is it possible to dissect a cube into a finite number of smaller cubes of different sizes? Oh, it turns out there's a simple proof of that. Basically, suppose it is possible, and then put the cube on a table, and then consider the smallest cube that's touching the table, and what is on the top of that smallest cube. Well, then you have a set where you have a squared square of some sort on top of that cube, since all the cubes are different, and since the smallest cube is surrounded by larger cube, there has to be smaller cubes on top of the smallest cube. And then you repeat the same thing you just mentioned with the table. Find the smallest cube that's touching that cube on top, and you wind up with an infinite series of smaller and smaller cubes. However, it is possible to make a very tight packing with different cubes of a cube. And here's an example for all the cubes 1 to 69 in a size 186 cube. So far as I know, this is the tightest cube packing that's been found so far. Another related problem that was discussed by Martin Gardner is the Mrs. Perkins's quilt problem, which was developed by Dewdney. You basically have a square and you want to divide it into smaller squares. However, you don't want the problem to be too simple. For example, with the 4x4, just dividing up into 4 2x2 squares, that would have multiple squares having, all the squares having the same lowest having the same greatest common divisor as a number greater than 1. So you want to divide it up into smaller squares, but the GCD of the sizes has to be 1. And the question is, what is the smallest number of squares you can do? And so here's some samples from Mathematical Carnival as shown by Gardner. And it's a deceptively difficult problem. This is one I decided to take a closer look at about 13 years ago. So I decided to find the best solutions for the Mrs. Perkins quilt problem based on a whole bunch of squared squares and squared rectangles from squaring.net. And I found that some of the quote unquote record-breaking solutions that couldn't be improved were actually wrong, because I found 16 different methods of building up these particular problems. And that was just basically an initial search. I found that there was basically a whole bunch of methods that showed up over and over again. So I just cataloged them and programmed them. And when I ran the program, I found improvements for just about everything. And unfortunately, that made me the expert on the problem. Anyways, these are the best results up to a certain size. Oops, and now this has decided not to work. Let's see here. Let's see if I can get this to work now. Hopefully it'll work. Yes. So there's a demonstration online that has all my best solutions. However, I haven't done a redo of this in 13 years. It'd be good for somebody else to look at my code for this demonstration, look at the 16 different building methods for building up and stripping down squared solutions, and to see whether there's been any improvements in the new solutions at squaring.net. So I mentioned Bouwkamp constructions. So here's one at 1216. The 12 means you're starting with with 12 squares, and the 16 indicates the size of the containing square. So this is 12 squares, 16 by 16, and then the rest of the numbers are the squares used themselves. So the first two, 3, 3, and then 5, 5. Next value is 6, and it goes to the leftmost position, and it continues from there. And this filling method, this particular format, was found to be pretty much optimal for compressing one of these diagrams. So one open question is whether there is a rectangle built out of consecutive squares. So far, there isn't one, but these are the best known solutions up to, I believe, 30. And this is a problem that hasn't been improved for about 15 years, I don't think. So it's solved up to 32. The solution for 33 squares, the smallest possible rectangle, is unsolved. So that's a good open problem for somebody to work. Another related problem involves taking a rectangle and any rectangle and finding any dissection into squares. Doesn't matter whether their GCD is 1 or not. You're able to do anything so long as you cover the square with or cover the rectangle with a minimal number of squares. So these are various examples. And the demonstration here has solutions up to, I think, 340 by 340. So one question with that is, well, you have a minimal dissection into squares. If you multiply the dimensions by 2, is it always the case that you need the same number of squares, or is it possible that there's with the larger size that there is a trickier dissection using fewer squares? Well, it turns out that I managed to find a few thousand possible counterexamples. For example, this one, here's a large rectangle using 21 squares, but if you go to a size that's twice larger, it only needs 20 squares. However, we're not sure whether this tiling is minimal because this is a difficult squared rectangle, but it's possible that if we're allowed a lot more leeway for how it's dissected into squares, it's possible that maybe there's a way of doing it with smaller squares. But solving that problem is extremely hard. That's why it's only been solved up to about 300 and something. So solving it for 5,000 right now is out of the question. So that's another interesting problem that's pretty much unsolved. Whether there's a faster way of solving this particular problem of dividing a rectangle into squares. And here is a demonstration of that, showing some of the rectangles. Oops. But since I've got so many different square related pieces of code, I start getting code clashes with these. So this, my coloring got lost here. So here's an example of a dissection that uses a fewer number of squares if you increase the size. I showed the crushed rectangles earlier. One thing I did was try to solve the Mondrian art problem with those, where I just took all the possible Blanche dissections and laid them out for different sizes and rounded off. Since the rectangles were usually distinct, and in different orientations, when rounded to a nearest integer, for example, I believe this is rounding to multiplying everybody by 138 and then rounding. The largest rectangle here has area 1,200 and the smallest has area 1,178. And the difference between those two is 22. The Mondrian art problem asks you to divide a square into different rectangles, non-congruent rectangles, so that, and with using integers, so that the largest rectangle and the smallest rectangle have the smallest possible difference. And it's unsolved whether the defect can be 0 or not. So using that method of using the Blanche dissections, I found a whole bunch of solutions up to size 60 or so, and most of those turned out to be correct. I didn't use enough planar graphs in my generator to find all the best solutions, so some of them were improved. And the let's see, the defect, if compared to this value, n over log n rounded plus 3, they're curiously close. The difference between that and the actual solutions, here's a plot of how that looks up to 60. So rather odd sequence. I also looked at a variant problem where I allowed rectangles to be repeated so long as they had a different orientation. So here's a strange solution where I divide up a square of size 45, where every rectangle appears twice in one in each orientation. I'm not sure whether a larger solution of this type is possible. And I also have a with this one, the upper bound seems to be n over log n straight, and this is what the plot looks like of the difference between those two values. So these this concept that Martin Gardner used of, or William Tupp used, of taking a planar graph and turning it into a rectangle diagram has different powers depending on how you look at the geometry. You can make a squared rectangle, or you can make a Blanche dissection where all the rectangles have the same area. There's also a few other tricks that you can do with those dissections, but they end up solving a whole bunch of different problems. So here are my solutions for the Mondrian art problem here. I believe I have solutions up to 1,000, but most of them over 60 are probably wrong. Most of them are probably improvable. A related item we can look at is rectangles packed into the same rectangle. For example, the golden ratio. If we remove a square from a golden triangle, we get another rectangle. But also, a series of square root of the golden ratio rectangles will make another square root of golden ratio rectangle, as shown here. Another value, the silver ratio, which is used in A4 paper, you can do a similar trick. When you fold A4 paper in half, you get two rectangles that are also similar. And you can keep doing that folding trick with A4 paper, and it'll always have the same ratio. One thing that wasn't known was that you can take these A4 rectangles and make a perfect dissection of an A4 rectangle using all squares and double squares to get back to a A4 rectangle, as shown here. And various other constants have that property, such as the super golden ratio and the plastic constant. And there's also many other constants that work. Basically, no matter how you set up the rectangles, if you go to like 4 or 5 rectangles, you can get many different solutions with using different constants. I mentioned the Ponting square packing. So here are squares 1 to 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. We can make a matrix of those like so. 1, 8, 2, 9, 3, 6, 4, 7, 5. And if you look at these lines, on each side of the line, you have the same sum. 7 plus 5 is equal to 3 plus 9. And when Adam Ponting found that, he just basically expanded the matrix to include all the numbers up to some size. As for example, and it's a rather simple arrangement. He goes 1, 2, 3, 4, 5, 6, 7, 8, 9. He just basically fills in the gray squares with all the numbers 1 to 41, and then he starts here and does all the numbers 42 to 81, 42, 43, 44, 45. And you can do that with any square number. You can basically split these up to go from a matrix where on either side of the line you have the same sum to a square packing using different size squares. And you get these strange curvy shapes out of the squares. With various modifications to the matrix, you can use different squares and get different shapes. And the one I started with at the start, the matrix still works if you use negative values. However, when you're drawing it, it's fine to use positive values. So the trick of using everything twice to make a loon just basically uses that trick of using the Adam Ponting matrix. And there's of course various different tricks that can be done with square packings. We can do orbits of various sorts. We can also hinge the squares. There's also ways of spreading the squares apart. One question I'm not sure of the best way of getting the answer for is, if you have the squares at different angles, what's the best packing for that particular angle? I don't have a clear way of solving that yet, but I'm sure that's not too difficult. One problem Barton Gardner mentioned that was later solved was the best way of packing squares with fractions, 1/2, 1/3, 1/4, and so on up to 1 over n. And the question was, is there a way of packing all these squares into a rectangle? At the time, doing it by hand, it was extremely difficult. But with a computer, it's not that hard to do. And Mark Paulus developed a simple algorithm. In fact, I can show it here. A splitting algorithm. He basically has a rectangle somewhere on the grid. He keeps track of them, and then he splits them carefully as necessary. Oops. Let's see if I can get my image back. So with those, we can make a whole bunch of different squared rectangles, getting very close to a total area of pi over 2 over 6 minus 1. And these fractions get closer and closer to that value. One type of rectangle which is difficult to divide up into squares is the oblong, where you have sides of rectangles of size n by n plus 1. So here are the best known solutions for dividing up various oblongs into squares. However, above this one and above, they're not known to be minimal. These are just the best solutions I was able to find. The brute force solving method would have taken me too long. There's also the classic Fibonacci spiral. So we start with this 2 squares of size 1. We add a square of size 2 on one on top of them, and then a 3 on the side, and then 5 below. And as you continue adding the squares, you get the Fibonacci spiral. And a similar method appears with the plastic constant, but here you use cubes instead. Let's see what it is at the core. So we start with 2 cubes, then we add a cuboid, then a cube, then another cuboid, then a cube, and so on. And we get the Padovan spiral. Unsolved, I mentioned some of them. Many of these problems just haven't been looked at for a while. So with a proper computer search, it's probably possible to improve many of these solutions. And as I showed at the start, some AIs are finding solutions for these. In fact, I mentioned the one for the cycle double cover conjecture that announced the solution just last Saturday. And that's what I had prepared for this talk. I'll be glad to answer any questions people may have. Just feel free to post any questions you have, and I'll be glad to try to answer them. Let me post something here. And if you want to look at the code for anything, it's all posted on community.wolfram.com. And you can also ask questions there if you have any. All right, many thanks for attending my talk. Thanks very much.